Hi guys, welcome back to Chem 223. This is our second part of statistics, where we'll be discussing the real G-test. Of course, this is a picture of Tupac Shakur, the original OG, and we'll also be discussing calibration curves. That's why I got a picture of California there. I think this is a pretty good intro slide. Anyways, we're going to start by talking about the G-test, and the G-test is used to look for outliers in data. So we're going to go back to our UNO data from our last lecture. So this is the UNO attack data. On the bottom of this chart, what I have here on the x-axis is the number of cards ejected, and on the y-axis I have the number of occurrences. So this is a histogram where I counted the number of cards that came out each time I pressed the button, and I plotted how many times we got each number of cards. So this almost looks mountainous, so it's almost Gaussian. It's not quite Gaussian. There's a little dip, definite depletion or noticeable depletion here for 5 cards. But the question here is actually going to be about this tail end data. So we see at 8 cards, we only had that happen once, and we also had 9 cards happen once. And so we're really going to question this 9 card data right here. Was this just because a kid was playing this game and happened to eat a jelly sandwich before this, full of jelly? When I was a kid, my oldest brother made one of my younger brothers a sandwich full of mustard for some reason, and that mustard got into our Sega Genesis and killed it. An interesting story, not relevant, but we're going to ask, is there something weird about this 9 card distribution measurement? So there's a few questions we're going to ask. The first, is there something obviously wrong? Like, did you see one of the kids putting jelly on the cards? Or in a lab sense, do you know that you added the wrong amount of chemicals? Did somebody stick their finger in there? Did you add the wrong chemicals? If there's something you obviously did wrong and you know it, then you can just throw out that data. All right. But if the answer is no, if you don't know that there's anything obviously wrong, it just looks suspicious because it's way too big or way too small numerically, then you have to do what's called a G-test. So the G-test looks like this, and it's I think our 4th lettered test. So we did the F-test last time, and we also did about 3 versions of the T-test. But now we're doing this G-test, and the way this is done is you take that questionable value. So in this case, that would be the 9. You subtract the average of all your values that you got, and you'll notice this is in an absolute value lines. So this top part will always be positive, and your G value will always be positive. And you divide that by the standard deviation of all of your measurements. So this standard deviation value here and this average value also include your questionable value in them. And then just like the T-test and F-test, you compare your calculated G value to a table G value, and you ask, is your calculated value bigger than your table value? If your calculated value is greater than your table value, that means that your questionable value is the statistical outlier, and you can reject it. Now, I don't actually know an equation for looking up or for calculating a G value in Excel, so we are just going to turn to table 4.6 in your book, and it has on one side number of observations, and on the other side the G value associated with a 95% confidence interval. Now for the G table, we're actually just working with number of observations here, not degrees of freedom. So in our UNO attack experiment, we took 68 measurements. So we have to go down on this table till we find, oh, 68 happens to be here. That's actually because I had to look up the value for 68 and add it to this table. Table 4.6 doesn't actually have that. But then we do our calculation of our G value. We plug in that questionable 9 value and subtract the average of all of our UNO values, which happens to be 4.89. And we divide that by the standard deviation, which was 1.44. I calculated these separately. You'll notice here that In this calculation, I leave more decimal places in my standard deviation, or in other words, I have 3 significant figures in my standard deviation. I'm not rounding that yet because we're in the middle of a calculation, so you want to keep those there. And we calculate out a G value of 2.85. We have to compare this 2.85 value to the value for G for 68 trials. We'll find that that value is 3.248, which is bigger than our calculated 2.85 value. So statistically, we can't say that that 9 is an outlier, and we have to keep it in our data. So a few comments about this. The first is sometimes people will calculate whether a data point is an outlier. They'll find it's an outlier, and then they'll throw it out. And then they'll look at the rest of their data, and now that that big outlier is gone, some of their smaller outliers kind of look like they're outliers. So they'll run a G-test again with the new data, excluding that first outlier, and they'll find that they can throw out more outliers. And then now they have a smaller set of data. They'll do their outlier test again, throw out even closer outliers. And that's actually illegal. You can't do that. You have to, when you're looking at outliers, you always have to include all measured values, even outliers you've thrown out previously. Otherwise, you are basically whittling your data down quite a bit. I'll also say that oftentimes in the lab, students think a data point is inaccurate because it's really far away from 2 other points. So oftentimes you'll take just 3 measurements and try and calculate an average and standard deviation from that. So they'll have 2 points that are really close together and a third point that's far away, and they'll think, oh, this is an outlier, I want to get rid of it. But oftentimes the true value is somewhere in the middle of those 2 values. And so if you throw out this outlier, then your actual value you calculate is pretty far from the average. And so oftentimes, if you keep all of your data and don't just assume there's something wrong with the data because it's far away from 2 other ones, then you're usually closer to the true average. And I actually see that every single semester. I see a student trying to throw out a data point, and because they throw out a data point just because it looks different than 2 others, it costs them tons of points in the lab. And literally every semester I see an example of that. So don't just throw out data because it's far away from other data. Our minds are built to look for patterns and look for groupings. And so the natural inclination is to throw out things that don't fit into the group, but often that's a mistake that costs you later down the line. It's also good practice when you make a measurement to look for other people that have made similar measurements to see how your data compares, whether your results are similar or different. So for this particular experiment, I went to the UnoAttack webpage. I have the link listed down here at the bottom of the slide. But this is what the website says. It says, try your luck. Press a button on the card launcher and it shoots out a random amount. Will you get stuck with 1, luck out with none, or get a dozen cards? Each turn is unpredictable, so take your chances. Now our results are somewhat consistent with this. I never got a 1 shot out at me or a 12, but we got a bunch of numbers in between. And it says that you can luck out with none. I actually did get none a bunch of times, but I didn't include that in my data. I was just looking for how much cards it spits out when it spits out cards. But so our results are basically consistent with this. I think they might be stretching the bounds of how many cards get shot out, but who knows? Maybe I just didn't sample enough of the actual population to know. All right, so to review, when we're talking about outliers, I often get this question in lab, both in the classroom lab and in actual research settings. Dr. Mortensen, one of my values is a little different from the others. Should I keep it or throw it out? The way I always answer this question is, well, is there something obviously wrong with it? If there is something obviously wrong with it, throw out that datum. Of course, datum here is the singular of data. Data is a plural. And so data from Star Trek, it was a pluralistic name for some reason. Anyways, if the answer is no, there's not an obvious problem, you'll have to do a G-test. always. There's no other magical solution. I can't just say, oh yeah, that looks pretty different. I would say throw it out. You always just do a g-test. All right, so this wraps up our Tupac Shakur portion of the lecture. We're now going to move on to calibration curves. What is a calibration curve and why do we need it? I'll start off with measuring the value of an unknown. So let's say I have a sample. It's got barium in it, and I don't know what the concentration of barium is. So I throw it in my atomic emission spectrometer, and I measure out a signal of 4.020 volts. What does that mean for my concentration of barium? Really, it means nothing with what I have so far. Really, I can't even look at this data and say that there's barium in there or not. I don't know what the baseline of this instrument is, how much noise it has, what the signal looks like without barium. So what I have to do to create a calibration curve, or I have to create a calibration curve to figure out what this information means. So what I do when I'm making a calibration curve is I prepare a bunch of standards of known concentration. I put them through the instrument and I measure their signal. Now you'll notice here I have a sample with a concentration of 0, and it gave me a signal of 0.006. And this is because the instrument itself has some amount of noise, like we talked about last time. It has some fundamental limitation where we can't measure the concentration of anything that's going to result in a signal that's less than the background noise of our instrument. You'll also notice that I keep increasing the concentration here until I have a sample that gives me a signal that's higher than my unknown value. And of course I have values, or have samples that return a signal that's lower than my unknown sample. Whenever possible, you want to encapsulate the signal of your unknown within your calibration curve. Now, that's not always possible, but when it is possible, you definitely want to make sure to do it. Okay, now we have all these data. How do we use this data to figure out the concentration of our unknown? Well, what we do is we take that data and we plot it. So on the x-axis here, I have concentration, and on the y-axis, I have the response from my instrument, so my signal. And you'll notice these data are mostly in a straight line. I don't know how well you can see this, but at the bottom here, you'll notice the data is coming down in a pretty straight line, but then it starts to flatten out. And that is because of background noise. So the background noise contributes a lot more to the signal for our concentration of 0 than it does for our concentration of 10. But we're going to then draw a line through all of these points and try and get a line that crosses through as many points as possible. And we're going to come up with some sort of equation for that. So this equation describing this line is just our standard y equals mx plus b. And because this guy starts to flatten out down here, we get instrument noise. That results in us having an intercept that is not exactly 0. And we get an intercept that is a negative value. So these guys, if there was no instrument noise, it would keep going down into this negative value. Hopefully that makes sense to you. If not, feel free to reach out or ask another student in the class, and we'll see if we can't sort you out. But then, now that we have our calibration curve with our our data plotted from our known samples, we will throw the signal for our unknown on the y-axis here. So our unknown gave us a value of 4.020 volts. We're going to draw a straight line from that till it intersects with our calibration curve line. And then from there, we're going to draw a straight line down until it intersects with our y-axis. And where it intersects is going to be the concentration of our unknown. So that's 7.89 milligrams per liter. But doing this visually, so trying to put a ruler there and draw a perfectly straight line in this direction, draw a perfectly straight line in that direction, and then figuring out exactly where that is hitting on this x-axis is not a great way to do this. So we have an equation here for our calibration curve, and we're going to use that to solve for where, or what our x value is for our unknown. So here we measured our y value. So we take our equation here for y equals mx plus b. We have the y value. From our best fit curve here, we have our slope and our intercept. We need to solve for x. So if we solve for x, that's going to be equal to our y value minus our intercept divided by our slope. So then we can just plug in these values here into that equation. And we solve that, and we get an x value of 7.89. Now you might be asking, why do we have 3 significant figures in this value? Why not 4, since we measured 4 significant values? Or it could be 3 because our intercept only had 3 significant figures. But the real answer to that is we have to figure out the uncertainty associated with this x value, the uncertainty that we get from going through a calibration curve. And the uncertainty associated with this value is a little more complicated and needs its own discussion, so it'll be the topic we discuss at the end. So what we're going to discuss right now is, how did I draw this line? How did I do it as best that I could? Well, we did this using what's called the method of least squares, right? And so for a linear relationship between the x and the y axis, that's just going to be a straight line, right? And so we're really just going to be talking about the method of least squares for straight lines in this class. Calibration curves can include x squared terms or 1 over x, etc. But we don't need to worry about that for this class, or at least not the math of it. All right, so I try and draw a line through these points, but you'll notice these points, they're a little more spread out than my points on my previous slide. So how do I get this line perfectly? Do I wiggle it up a little bit to get it closer to this guy? Do I wiggle it down so it makes sure to cross through this point? Well, really what we try and do is we try and minimize the vertical distance between each of these points and the line. And really what we do is we measure the distance here, and then we square it, and we add that all up. Then we wiggle the line a little bit, and we measure the distances again. We square them and add them all up and say, did that value get bigger or smaller? And really we want to keep doing that until all those values minimize. Now, obviously doing that by hand is silly, and so statisticians came up with just some simple equations that'll do that for us. And when I say simple, I mean really ugly, nasty equations. But we're going to talk about that. Before we do, let me throw out a quick question here and ask where on this calibration curve is most accurate. And the answer is it's going to be right in the middle of this calibration curve, where you get the most accurate measurements and data. Why is that? Well, because if you remember what this guy looks like when he's wiggling, if you wiggle it a little bit up here, well, if it's wiggled down a little, your value up here is going to be down here. If you wiggle it up, it's going to be way up here, right? But if you look at the middle of this line, it's not moving nearly as much. So the farther away you get from the center, the more that wiggle or that uncertainty in where we put this line is going to matter. And you don't have to take this or my word for this. Elder Bednar's also spoken on this, so we'll let him give his 2 cents.
Although both were experienced pilots, neither had made this particular flight before, and they had no way of knowing that the incorrect coordinates had placed them directly in the path of Mount Erebus. It was a terrible tragedy brought on by a minor error, a matter of only a few. Through years of serving the Lord in countless interviews, I have learned that the difference between happiness and misery in individuals, in marriages,
and calibration curves
often comes down to an error of only a few degrees.
Thanks, Elder Bednar. I agree. All right, so how do we actually figure out that best fit curve so that it gives us the least amount of error? Well, we're going to have to use some equations. And like I said, these guys are pretty nasty. This is the equation for determining the slope of your line. So M here is equal to the number of measurements in your calibration curve, the number of points in your calibration curve, times the sum of all the X and Y values multiplied together. So this would be x1 times y1 plus x2 plus y2, etc. And I will work out a problem in front of you so that you are really clear on what I mean by this. Then you have to subtract the sum of all the x values in your calibration curve times the sum of all your y values in your calibration curve and divide by this d term. Now this d term is defined like this. So it's the number of points on your calibration curve times the sum of the square of your x values. So you have to square x1 plus the square of x2 plus the square of x3, etc. And then you subtract the square of the sum of all the x values. So here you square the x values and then sum them. Here you sum the x values and then square. Right, and the reason we give d its own little equation down here is because we actually use it a lot. So here is the equation for calculating the intercept of our best fit line. And you'll notice that the d term is on the bottom here too. And on the top, we have the sum of our x values squared times the sum of all of our y values minus the sum of our x times y values times the sum of our x values. Okay, so just to be clear what we mean here in each of these instances, we're going to work through some data. This is actually real world data. So Dr. Macedonia in our department purchased a car a few years ago. And from what he says, this is really old data now. But in the first year, he bought it. So when he very first bought it, the car had 61,852 miles on it. And every year around the same time, he measured the odometer. Yeah, I think it's the odometer, right? Now you're discovering Dr. Mortensen knows very little about cars. All right, but he measured the mileage. And as you can see, his mileage was pretty linear, meaning we could draw a pretty straight line through this. He used about the same number of miles each year. So let's take this data now and turn it into a best fit line. All right, so what I have here are our x values and here are our y values. So this value for 0 would be x1, the value for 1 would be x2, this would be x3, x4. And over here we have y1 is 61,000 miles, y2 is 72,000, y3 is this 80,000, and y4 is, or sorry, y3 is this, oh yeah, sorry, y4 is this 94,000 value. Okay, so let's look at what we need to calculate here. So we need to calculate our D, M, and our B, and all of the sums in these equations are actually listed here. I've placed these conveniently for calculating them. So we have to sum up the x values, sum up the y values, sum up these other two terms. So let's start with summing up the x and the y values. So to sum up the x values, this is 0 plus 1 plus 2 plus 3, and that equals 6. For the y values, we have 61 plus 72 plus 83 plus 94,000, which equals about 312,000. Okay, so these ones, fairly straightforward what we're looking for. Now let's calculate this sum, the sum of our xi times yi values. So this doesn't mean we're taking every x value and timesing it by every y value. This means that we're going to take x1 times y1 and add that to x2 plus y2, etc. And then for our xi squared values, we're just going to square these guys. So let's look at what that looks like. So xi yi for x1 times y1, we have 0 times 61,000, which is 0. For x2 times y2, we have 1 times 72,000, and that equals 72,000. And we keep going down that to calculate these other values. For our xi squared, we're just going to be squaring the x values. So 0 squared is 0. 1 squared is 1, 2 squared is 4, 3 squared is 9. And then we're just going to take each of these columns and sum them up. So 1 plus 4 plus 9 plus 0 is 14. Then for our xi, yi values, we just add all these guys up to get 523,816. And then calculating our d value, I got a value of 20. For M, I got a value of 1,000 or 10,886, and for B, I got a value of 619.01. I got a value of 619. I got a value of 61,901.3. All right, so let's look at these values. Go ahead and pause the video right here. See if you can't work through these values and calculate D, M, and B, and I will go through these with you in a minute. See if you got them right. Okay, now we've got these values calculated out. Let's talk about our uncertainty in our line that we put. You'll find the more and more we do measurements and calculate values, the more and more uncertainty we discover. All right, so first, let's describe the uncertainty in the vertical positioning of our best fit line. So that's what we call our SY value, and this is just asking, with our best fit line, should we move it up or down on the y-axis? And how confident are we with where we put it? So this is calculated by taking the square root of this sum of our DI values squared. And our DI here is just equal to our Y of any point on our calibration curve. So this is the measured value for a standard minus the slope times the X value of that standard minus the intercept. So this Y and X, so the X is our value that we made. So this is the concentration we made. Our Y value is the signal response we got for that sample, or that standard. And then M and B are the slope and intercept calculated from our linear regression. So for a perfect fit, this D value should be 0. But if our Y value deviates at all from our best fit line, then this is not going to be equal to 0. Okay, at the bottom of our S sub Y value here, we have N, which is the number of points on our calibration curve, minus 2. We also have an uncertainty associated with our slope. So S sub M, that's going to be equal to our S sub Y times the square root of the number of measurements, or the number of points on our calibration curve, divided by this big D, which is the D from our previous slide. And then we also have an uncertainty in our intercept. This is our S sub B, and that's going to be equal to our S sub Y times the square root of the sum of the square of our X values divided by D. Now all of these values are valuable to us. That's why we call them values. But calculating these things and calculating the slope and intercept by hand becomes very tedious, especially when you get a calibration curve with 100 points on it or so. And so I'm going to show you now how to calculate these data using the linest function in Excel. I'm going to do this using some real-world data. So this is data that I collected when I was trying to measure how much two solutions mixed. So in this experiment, we had two glass capillaries or barrels lined up side by side. And we had solution flowing through these. And at the end of the barrels, these solutions would mix. And we were trying to measure how much they mixed. So in one barrel, we put this molecule that's called 18 crown 6, and we put sodium in there. And in the other barrel, we put potassium. So 18 crown 6 forms complexes with both sodium and potassium. Those complexes just look like this, where 18 crown 6 forms a ring around our ion here. And then the oxygens dipole bond, or have dipole interactions with our ion here and stick. So these are at equilibrium. So not all of the 18 crown 6 forms this complex. So some of it is still free. And if these two channels mix, then some of that 18 crown 6 will bond with this potassium and will form this complex. So we can measure how much mixing we're getting by looking at the relative ratios of these two species. So let's jump over to our spreadsheet really fast, and I can show you how to calculate all these functions using linest. So what we have here is the concentration of potassium. And over here we have our ratio between the sodium and potassium complexes. So this would be our X data, or our X values. So here on this plot I have our concentrations. And on the Y value I have the signal response, or the ratio between these two species. So let's find all of those values here. We're going to find our slope, our uncertainty with our slope. We're going to find our intercept, our uncertainty with that. We're also going to find our uncertainty in our y value, or our y positioning, so our S sub y. The way we're going to do this is we're going to highlight a bunch of cells in here, and we're going to type equal linest is our function. We're going to put a parentheses. We're going to highlight all of our y values here, comma, all of our x values. We're going to put in another comma, and it's going to ask us for a constant. And this is a true-false statement. So it's asking us if we put false, it's going to set our b value, or our intercept, equal to 0. And if we say true, then it's going to calculate our intercept like normal. So we're going to say true here because we want our intercept. We're going to put another comma, and now this function is asking, do we want to calculate other statistics like our S sub m, S sub b, etc.? We do, but it becomes cumbersome to type true a bunch of times because you're going to be using this function a lot throughout the semester. So let's not type true, let's type 1. So 1 is equal to true, 0 is equal to false. So we're going to put a 1 here. I will close that parentheses. And now what you're going to do is you're going to hold Control, Shift, Enter. And that is going to fill all of these boxes. The reason you have to hit Control, Shift, Enter is because this is what we call an array function. An array function fills multiple boxes. And Excel doesn't know that this is an array function until you hit Control Shift. And that's the code that tells Excel, I want this to be an array function. So let's do this again where we highlight all the cells. We type in linest. We highlight our y values. We highlight our x values. We type 1 for true, 1 for true. We close this parentheses. And now we hit enter and we forget to hit Control Shift. What happens? It just fills one box. And that's because we didn't tell Excel we want to fill the entire array. All right, now let me fill this data back in with the right stuff because we will need it in a second. So we have our y values, we have our x values. We're going to put 1 for true, 1 for true, close this up, hit Control Shift and enter. Now let me talk about these other values that it calculated for us too. So right here we have this r squared value. R squared tells us how good of a fit this is. R squared theoretically ranges from 0 to 1, but I've gotten it to go to -2000 before. So a 1 for an R squared value means that you have a perfect fit for the data. Right now this is showing 1.0, but if we show a few more decimal places, you'll notice that it's not a perfect fit, right? And if you look at this plot over here, some of these points are slightly below the line. Some of them are slightly above the line. But a fun trick is if you just reduce the number of decimal places in your R squared value, you can make it look great. So generally it's, you report it to at least 2 or 3, but it's usually pretty obvious how many you reported to. All right, now the rest of the stuff on this slide we will come back to, or on this spreadsheet we'll come back to in a minute, but that is how you use the linest function. All right, now I'm gonna jump back over to the PowerPoint here, and we will now talk about the uncertainty in that data. So specifically the uncertainty in our x value we determined for our unknown. So if you remember, when we calculated an x value from a y value from our unknown, we drew a line and we drew down and we had that point. But what is the uncertainty that results from going through a calibration curve? Well, the uncertainty, or the S sub x, looks like this. It is a very ugly equation, and unfortunately there's no shortcut in Excel to calculate it. Now there are a lot of things in here that Excel can calculate for us, like our S sub y and our slope, but we still have to type this whole equation in. So let's go over real quick what all these things in here are. So our S sub y is just our uncertainty in y that we just talked about. Our m is our slope. And then in here we have 1 over k, where k is the number of replicate measurements we take of our sample. So if we take our unknown and measure it 3 times, then k here would be 3. The more times we measure our unknown, the more our S of x is going to go down just because of that. Then we add that to 1 over n, where n here is the number of calibration points we have on our calibration curve, and that would include our blank. So if we put in something with 0 concentration, we get to include that too. So the more points you have on your calibration curve, the more your uncertainty in x decreases. Now up here on the top of this fraction is probably the most confusing part of this equation, because we have two y's here. This y is the average of your unknown response values. So if you measure your unknown 3 times, you take the average of that, and that's this y. But this y right here actually refers to your calibration standards. So this one is your unknown, this one is your knowns. And what you do here is you just take the average of the y values for your standards. So your average signal response for all of your standards. So you take the difference of those two values and square it, and then on the denominator down here, you have your slope squared times the sum of your xi minus x bar values squared. So this square is inside the sum. So what this means is for each calibration point, you take the x value of that calibration point and subtract the average x value of all of your calibration points. And then you square that value, and you do that for each point on your calibration curve, and you sum that up. So we will go through calculating this together, just so hopefully it's clear what we do. All right, and we're going to start with this real world data, but we're going to throw in some unknown values. So I took an unknown, measured it 3 times, and these are the values that I got for it. And now I can't actually remember if these are real unknown values. I think they are, but I can't remember right now. Anyways, we're going to take these values and we're going to ask what is the concentration of our unknown, and we're also going to ask what is the uncertainty in the concentration. Let me ask really fast, why if I took the exact same unknown 3 times, measured it, why did I not get the same value each time? And this goes back to what we talked about before with instrument noise or with fundamental limitations of our instrument. Every time we measure a sample, we're going to get a slightly different value. Part of that is the fundamental limitations of the instrument. Part of that is our own limitations in preparing samples, etc. But we always get some uncertainty. All right, so let's talk though about the uncertainty in the concentration, and that's going to be calculated with this equation again. So we're going to jump back over to the spreadsheet really fast, and you will notice that I have that equation written right here for us. I'm not going to type all of this in at once because, or at least not at first, because there's several of these values that we don't have yet. So from our linest, we did get our S sub y right here. We do have our slope. For k and n, we'll just have to count that. But let's calculate all these other guys. So we'll start with y here. So if you remember, y is the average of our unknowns. I'm just going to use this average function. So that's just equals average parentheses. I highlight my unknown values. I hit enter, and it's calculated that for me. For my y bar, I am going to again calculate an average here. But this is the average of the y values from my calibration curve. So I'm going to take all of these. And now I will calculate my x bar, which is similar to my y bar, except of course it's the x values. Now let me pause here to point something out. So with these values, I do have this formatted to show a certain number of decimal points. But if I calculate something from these values, so for example, I'm going to use my S sub y in this equation, even if I reduce the number of decimal points, Excel will still look at the whole number. So even if you format things in Excel, you're still not rounding, so you don't have to worry about losing decimals by formatting these to look properly. All right, but now let's calculate this part, the sum of my x values minus x bar squared. Now I could calculate this all in one cell, but it's going to be really complicated. So I'm actually going to calculate this in a few cells. So first, I'm going to take my first x value, and I'm going to subtract my average x value here. I'm going to go ahead and hit F4 on my keyboard to lock those in as constant values. So it will always be looking at these. Just to review, if I hit F4 again, it'll make it so now the dollar signs are just on the numbers. So if I dragged this cell right or left, it would change which column it's looking at, but it won't change the numbers. If I hit F4 again, now it just puts the dollar signs on this B column. So if I drag this down, it'll change what numbers I'm looking at, but it won't change which column I'm looking at if I drag it right to left. But I want to hold all of those constant for this. And then I need to close my parentheses. And I'm going to square the difference here between x1 and the average of the x values. Now I'm going to take that number, I'm going to drag it down like this. So now this value down here is looking at the difference between 10 and the average of all of these guys squared. So we have all those now. And then for our sum, I'm going to just use the sum function. So it's just equals sum, parentheses, highlight these guys, hit enter. Now I have that. So I have all of the data I need to calculate this big equation right here. So I'm going to come up here and calculate my concentration first. So if you'll remember, this is just calculated from our y equals mx plus b equation. We got to solve for x because the concentration is on the x value. So I am going to do my y value, my average y value. I'm going to subtract my intercept here, and then I am going to divide all of that by my slope. I get a concentration of 3.86. And just to highlight what I was talking about before with my intercept here, I have it formatted to just show one significant figure. But if I move this to show more, you'll notice my concentration isn't changing at all. But if I change other values in here, so let's say I change this 52 to a 72, well, that does change my concentration value. I'll change this back real fast. All right, so now let's calculate our uncertainty. So I'm going to do equals our S sub y value right here, divided by, I need the absolute value of the slope. Now, since this is positive, you might not worry about it, but if it's ever negative, let's just do this the right way so you'll know how to do it. We're going to use the absolute value function, which is just ABS in parentheses. I'll click on my slope, close parentheses. Now I'm going to have to times this by the square root of all of this. So I'm just going to type square root, or SQRT. I'm going to put a parentheses. Then I will do 1 over the number of unknowns I did. Now I can do this two ways. I can just see that that's 3, type 3. Or I could use the count function here. I just type in count, highlight those, and either way it'll work exactly the same. And I'll do 1 plus 1 over n. So that's plus 1 divided by the number of points on our calibration curve. I'm feeling lazy, don't want to count these, so I'll just use the count function. Personally, I generally use the count function for everything because I'm pretty lazy and it just is a lot quicker than actually counting most of the time. When there's only 1, 2, or 3 numbers, obviously it's often faster to just count them visually, but I tend to just use count for everything. All right, now we have to do this part. We're going to do y minus y bar. We have our y value here. Subtract y bar, which we already calculated here. We're going to square that value, and then we have to divide by this denominator. I'm going to put this whole denominator in parentheses because we're going to be doing our slope squared times this value right here that we calculated over here. We're going to close up our parentheses. I doubt you can see this on your video, but each of these parentheses has a different color. And so the closing parentheses and opening parentheses all match each other in color. And another trick to see where the parentheses go is if you click up here on the equation bar, every time you click through a parentheses or move through a parentheses, so I'm just hitting my arrow to go over a parentheses, it will highlight that parentheses and its corresponding opening or closing parentheses. So that can be really convenient to tell where your parentheses are looking. I'm going to close this guy too, and that should finish up all my parentheses. I hit enter. So now I know that my concentration is 3.86301, and my uncertainty is 0.3237. Now, how many significant figures should I have in my uncertainty? It should be 1, so I can format that like this. Now I have to ask how many decimal places do I have? I have 1 decimal place, so now I need to format my concentration to also only have 1 decimal place. So I have 3.9 plus or minus 0.3 as my concentration. Now, of course, a different way of doing that is I could just highlight both of them and change the number of decimal places manually. Now, the way I changed from having it formatted with decimal places to without is there's this button right here. It's labeled as number. So right now these are formatted as numbers. If I click on this, I can also format them as general boxes. That's the general formatting for anything in Excel. There's a few other options. There's currency, so you can do that as money. If you want to do it as a date or time, you can also do it as a percentage. That's definitely not useful right now, but it can be in the future. There's also scientific notation, so this will calculate scientific notation for you. But remember, you should never report your uncertainty in scientific notation and have your concentration in another notation. So generally, it's best to report these as numbers. It just has them look the best, easiest to read, etc. Okay, that should be it for this lecture. If you have any questions, feel free to reach out and let me know, or feel free to start a discussion on the digital dialogue tab on Learning Suite. All right, hopefully that was helpful for you. Have a good one, and I will talk to you later.